This webcast discusses electric charge and the methods that can be used to create an electrically charged object. Electric charge is a physical property of the particles that make up all matter. An electric charge can cause two types of reactions, either an attraction or a repulsion. We're talking primarily about electrons and protons. An electron has a negative charge and a proton has a positive charge. The amount of charge on either a single electron or a single proton is written as a lowercase e, and it's called the elementary charge. It's called elementary because this amount of charge is the smallest amount that has ever been isolated. An electron has a negative charge, and so you could write that as negative e. A proton has a positive charge, and you could write that as plus e. Some subatomic particles, called quarks, may have charges that are fractions of this elementary charge, but this is still a theory, and these quarks have never been isolated to the point that their charges could be measured. The standard unit for measuring charge is called a coulomb, and that's represented by an uppercase C. An electron or a proton has a charge of magnitude E, where E is the elementary charge. The elementary charge E equals 1.602 times 10 to the negative 19th coulombs. This number is very important to us, and so it might be a good opportunity to pause this webcast and store this number in your calculator under the letter E. So E equals 1.602 times 10 to the negative 19th. That is the charge of a single proton, and it's also the charge of a single electron. So coulombs is a new unit of measure that we haven't discussed before, and I thought it might be helpful to try to get a feel for what is a coulomb of charge. So you know atoms are very tiny, and so the elementary charge, the charge of a single electron or a single proton, is very small, right? 1.602 times 10 to the negative 19th. That means that it takes an enormous amount of electrons or protons to be present to have a coulomb of charge. And I've written the number here. I don't really know how to say it. There are so many zeros. If you have a 100-watt light bulb, roughly 0.8 coulombs of charge are flowing through that 100-watt light bulb every second. And if you think about a bolt of lightning typically has about 25 coulombs of charge. So you don't need to remember any of these, but I'm just trying to give you a sense of what a coulomb is. So all matter contains a large number of both electrons and protons, and it's very common for an object to be electrically neutral, which means that the object has the same number of electrons and protons. So the positive charge of the protons is balanced by the negative charge of all of its electrons. It has a net charge of 0. Electric charge is caused by either adding or removing electrons. So if an object gains electrons, so that it now has more electrons than it has protons, that object now has a negative charge. If an object loses electrons, so that it is left with more protons than it has electrons, that object now has a positive charge. So both of these conditions are caused by electrons moving. the protons are in the nucleus in the center of the atoms, and they do not move except under very extreme and unusual conditions. For example, when you split an atom. So only electrons move. Here are two useful, simple formulas. If you have an atom and you know the number of protons and the number of electrons in that atom, you can calculate the charge of the atom by taking the number of protons and subtracting the number of electrons. Also, sometimes we want to know how many electrons had to move to give that object this new charge. So if you have the change in the charge of the object, the delta Q is the change in the charge, and if you divide by the elementary charge, E, then you can find the number of electrons that had to have moved. If the delta Q is negative, that means that the charge of the object became more negative, then that object had to have gained electrons. If the change in the charge is positive, then that means that the object must have lost that number of electrons. Remember, in physics, the change of any quantity equals the final minus the initial. So delta Q would be the final charge minus the initial charge. Electric charge is a conserved quantity, and the net charge of a system can be positive or negative or neutral. You can observe charge moving between the objects in a system, but the net charge of that system has to remain unchanged. And charge is said to be quantized. This word is important. Charge is quantized. That word means that charge always is observed as an integer multiple of E, the elementary charge. So an object can gain 3 electrons, for example, but it cannot gain 2.5. When it gains or loses electrons, it has to gain or lose whole electrons. And so therefore, the number of electrons changes in integer multiples. There are 3 types of materials that we want to discuss. A conductor is a material in which electrons are very loosely bound to the atoms in that material, and therefore there are some freely mobile electrons that are allowed to flow throughout the object. Examples are most metals, such as copper, aluminum, or gold. An insulator is a material in which electrons are very tightly bound to their atoms, and therefore the electrons cannot flow very freely. The electron cloud might shift slightly, but the electrons cannot leave their atoms. Examples are paper, glass, air, rubber. And then we also want to talk about objects that can be a ground. When we say that an object is ground, we mean that it's so large, for example, compared to another object, that it can absorb or supply an essentially unlimited number of charge carriers while remaining electrically neutral. The Earth is a common ground, but depending on the size of the system, you yourself could be a ground, right? Your body could absorb a lot of electrons before your body has a detectable electric charge. There are 3 methods for creating electrically charged objects. Friction, which means rubbing 2 materials together, conduction, and induction. All of these methods involve ways for neutral objects to become charged by either gaining or losing electrons. We'll talk about each method one at a time. So friction refers to a method of creating electric charge where two objects are rubbed together. The two objects might initially be neutral, right? Neither one of them has to have a charge at the beginning, but when you rub the materials together, electrons can move from one object to another. The object that gains electrons now has more electrons than it has protons, and so it has a negative charge. And the other object must have lost those electrons, and so it now has more protons than it has electrons. It now has a positive charge. We saw a good example of this method for creating charged objects in the sticky tape lab. When two pieces of tape were rubbed together and then pulled apart, the bottom tape gained electrons and became negatively charged. The top tape lost electrons and became positively charged. The second method for creating electrically charged objects is called conduction. If you're going to use conduction to create a charge, you have to start with at least one charged object. So friction worked even when both objects were neutral at the beginning. But for conduction to work, you have to start with at least one charged object. When that charged object touches a different object, electrons will move from the object with the greater negative charge to the other object. The electrons will continue to move until there is no longer a difference in charge between the two objects. The third method for creating an electric charge is called induction. Now, induction is a method that can allow objects to become charged even without ever touching each other. This is a two-step process. In the first step, a charged object needs to be brought close to a neutral object that is made from a conducting material. So when the charged object is close to the conducting object, the conductor becomes strongly polarized. It has freely mobile electrons, which are able to move to one side of the object. In the illustration at the bottom of this slide, we're looking at a negatively charged sphere that's being brought close to a metal rod. Now, initially, when they're far apart from each other, the metal rod is electrically neutral, and its positive and negative charges are evenly distributed throughout the rod. You see that on the left. But when the sphere comes close to the rod becomes strongly polarized. Its freely mobile electrons are repelled by the negatively charged sphere, and so they migrate to the far side, to the right-hand side of the rod. That leaves a positive charge on the left-hand side of the rod, because that section of the rod has lost some of its freely mobile electrons, and the rod has a negative charge on the right-hand side, because that side of the rod has now gained a lot of electrons. Okay, but at this moment, at the end of step 1, the rod is still electrically neutral overall. If we were to pull that rod away from the negatively charged sphere, the rod would go back to having all of its charges evenly distributed. So in order to create a permanent charge on the rod, on the metal rod, that rod has to be touched to ground to actually allow electrons to move either into the rod or out of the rod. And so I'm going to show that on the next page. So we could actually create either a negative charge on the rod or a positive charge, depending on which end we ground. So in the top picture, the ground is touched to the right-hand side of the rod. And so there are excess electrons on that right-hand side of the rod, and those electrons seek to escape. They see a place in the ground where they can move to a friendlier environment, and so they leap to the ground. When the electrons leave the rod, now the rod is not neutral anymore. It has more protons than it has electrons, and so it does have a net negative charge. Notice that you had to ground the rod while it was polarized. So this has to be done while the sphere is close to the rod, because that sphere being close to the rod is what caused the polarization in the rod. If you grounded a neutral rod where all of the charges were evenly distributed, electrons would not move because the Earth is neutral and the rod is neutral. Okay, so the top picture shows electrons leaving through the ground wire, and so we're creating a positively charged rod. But we could also do something like in the bottom picture. Here, while the metal rod is polarized, the ground could be touched to the positive end of the rod, and that would cause electrons to flow from the Earth into the rod. So now the rod overall is gaining electrons, and so the rod will be left with a net negative charge.